In this short video, we are going to discuss a problem on MM1 Infinity FIFOQ. So it is an infinite server model. Customers arrive at a one-man barber shop according to a Poisson process with a mean inter-arrival time of 20 minutes. Customers spend an average of 15 minutes in the barber's chair. If 1 hour is used as unit of time, then first subdivision, what is the probability that a customer need not wait for haircut? So when we consider this, it is a one-man barber shop. Therefore, number of servers is 1, hence it is single server system. The number of customers who enter the shop, there is no restriction on this. Hence, the capacity is infinite capacity. From the data that is given, the inter-arrival time is 20 minutes and the time that a customer spends in average is 15 minutes. With these detail, when we proceed, our mean arrival time our mean arrival time equal to 20 minutes and mean arrival rate lambda will be 1 by 20 per minute. The same thing would be 1 divided by 20 into 60, that is 3 per hour. Then the mean service rate given is 15 minutes. The mean service rate given is 1 by 15 per minute. Why did I make it as 1 by 15? Mean service time, the mean service time is 15 minutes. Therefore, mean service rate will be mu, which is 1 by 15 per minute. The same thing in hours will be 4 per hour. From these two data, we can find the throughput rho, which is given by lambda by mu. The value for the problem is 3 by 4, and you can see it is strictly less than 1, confining to the validity of the model. Then, what is the probability that a customer need not wait for haircut? When he will not wait? When there is nobody. That is, it is given by the notation P naught equal to 1 minus rho or 1 minus lambda divided by mu, which is equal to 1 minus 3 by 4 equal to 1 by 4. Since it is a probability, we have no units attached to it. Come to the second subdivision. What is the expected number of customers in the barber shop and in the queue? So expected number of customer in the shop is given by the number in the system, that is LS. Now what do we know? LS is given by rho by 1 minus rho. This value is 3 by 4 by 1 minus 3 by 4, giving us the value of LS to be 3. Hence, expected number of customers in the shop is 3. Similarly, expected number of customers in the queue. Expected number of customers in the queue. The notation that we generally use is LQ, and LQ equal to LS minus rho that is ls minus lambda by mu, that is 3 minus 3 by 4, which is 9 divided by 4. This is roughly 2.25. Having got these two values, the third subdivision is how much time a customer can expect to spend in the barber shop. This is given by the waiting time in the system. The waiting time in the system. This value will be given by the notation Ws. So Ws equal to 1 by lambda of Ls using Little's law. This is 1 divided by 3, and from the previous slide we have Ls equal to 3. So 1 by 3 into 3. So waiting time in the system is 1 hour, or it is 60 minutes. We should be careful to give the correct units appropriately for the subdivisions. In the fourth subdivision, we need to find average time that a customer spends in the queue. The average time that a customer spends in the queue is given by waiting time in the queue. Waiting time in the queue. The notation used for the purpose is WQ. WQ equal to 1 by lambda into LQ. WQ equal to 1 by lambda into LQ. This is nothing but 1 by 3 into 2.25, that is 0.75 hours, or in other words 3 by 4 into 60, that is 45 minutes. I once again remind you, we have to be careful about the units that we give. The next subdivision, what is the probability that there will be 6 or more customers waiting for service? We know that the probability of having n greater than equal to k, that is probability of having k or more customers, is given by rho power k. Here in this problem, k equal to 6, lambda equal to 3, and mu equal to 4. Hence, I need to find rho of n greater than equal to 6, that is 3 by 4 whole power 6. Once calculated, this value turns out to be 0.1779. There are no units attached to it, as this is once again probability. We are talking about the probability of n greater than equal to 6. I suppose you would have clearly followed the problem. Thank you for your patience.